Hello everyone. Now we are going to look at access to files, and first we are going to start off by looking at what exactly do you need files for, and then of course we will be looking at how do we manipulate files using the functions that are provided to us by the C programming language. Now in addition to that, in this unit we will also be looking at a slightly unrelated topic, which is manipulating bits. These are not directly related, but they sort of come together in one unit, right? So the overall outline, like I said, there will be sort of two distinct topics that we will be looking at in this unit, but of course you could break them up and look at the individual lectures on their own. In the first part we will be looking at files and I/O. So I/O is basically an abbreviation or a short form for input output, and in particular we are going to be looking at functions that are used for reading and writing from text files, and we will also contrast that with reading and writing binary files, right. It turns out that when you actually need to store data directly in some kind of binary format, there is a slight difference that you need to take into account. That is something that we will sort of try and understand why we need to even think in terms of binary and what the differences are that come about when you try to manipulate binary files. In the next part of it we will be looking at some aspects of bit manipulation, some of the functions and operators provided in the C language for manipulating numbers at the bit level, and this in particular becomes important in certain kinds of situations, especially with regard to embedded systems, because very often we need to take a multi-bit value, let us say a 32-bit integer, and set or clear or check the values of individual bits within that 32-bit value. And these bit manipulation operations become very useful in that context. Now in order to understand what files are, let us first look at it from a high level, the big picture, and try and understand a contrast between a file and memory. So we already know that in general in a computer there is of course the CPU, which does the actual work, that is to say it executes instructions, and our assumption is that the CPU has access to a large amount of memory, right, and this memory is required because the internal storage of the CPU, the registers that are used in order to hold values temporarily while the computation is being performed, are necessarily limited in number, and the moment that we want to sort of expand that and access more and more data, you need some better ways of handling it. Now typically in a modern computer the memory that is available is usually called RAM or DDR RAM, right. The DDR is particularly for double data rate RAM, and RAM itself stands for random access memory. Now the DDR and RAM are essentially sort of holdover terms. At the end of the day, what matters is that they provide a significant amount of relatively fast storage that the CPU can access. And in most modern computers, for that matter even in phones, the RAM that is available is typically on the order of at least several hundreds of megabytes, and usually in the range of gigabytes, right. And the way it is organized, we think of it as one linear array of data, right, ranging from low memory to high memory, and that individual locations within this memory can just be accessed by giving an appropriate address corresponding to the memory, right. Now this is good when we have gigabytes of storage. One of the issues with it is that it is what is called volatile memory, meaning that when you turn off the computer, whatever is in this RAM essentially gets reset, right. It becomes an unknown value, it may go to 0 or it may not, but the bottom line is there are no guarantees on what the value is going to be. Now what happens when we actually want to save data for a longer duration of time, right? And it turns out that you can sort of have access to what we call external storage, which is typically on the order of several terabytes, right. And external storage is something that is also connected to the CPU in some way, typically through the bus, and ultimately whatever access the CPU gets to external storage is by in fact loading data from external storage into RAM and then from RAM into the registers, right. So the external storage is typically orders of magnitude more than what you can have in terms of the internal RAM of the system, which in turn is of course orders of magnitude more than the capacity of the registers and the cache memory that is present inside the CPU. So why would we need this? Any kind of storage that we think about, any documents, any videos, any photographs, anything that we want to sort of retain in a digital format over time has to be in some format in a persistent storage, and that is essentially what the external storage is for. And as you could imagine, right, the moment we have a large number of, let's say, photos and videos and so on, even gigabytes of storage may not be sufficient. You may need to head towards terabytes of storage. Ultimately, of course, you go to data centers and companies like Google and Facebook and Microsoft who are actually managing the accounts of large numbers of people and they are now handling orders of magnitude more than terabytes, typically on the petabytes, possibly even exabytes of storage, right. That is not really something that concerns us at the moment. We are primarily interested in a single system where typically you would in the modern day encounter terabytes of storage. Okay. So what does that mean? One of the things that we need to understand about the storage is that storage can be thought of as a hierarchical system, right. You have the on-chip registers that are present inside the CPU. These are fast, meaning that they operate pretty much at the speed of the processor. So in one clock cycle of the processor, you can access either read or write a given register. But on the other hand, that also means that they are small in capacity. The total, including what is called the L1 cache and so on, is typically on the order of kilobytes. And if you restrict yourself only to the registers that are present inside the system, that's not even kilobytes, that's probably hundreds of bytes, that's all that we are talking about. Okay. So in order to make up for that, we have what's called the dynamic RAM. The reason it's called dynamic is because it turns out that from the technological point of view, right, it is easier to create gigabytes of a certain kind of memory which is dynamic, and the sense in which it is dynamic is that it relates more to how you actually go about accessing it at the electrical level, right. So for most practical purposes, as a user of a computer, you don't really need to care about why it's called dynamic RAM. What does matter to you is to know and to be aware of the fact that DRAM or dynamic RAM in general is slower than the registers that are present inside the CPU, but can be of significantly higher capacity. Typically gigabytes are common these days. And of course, as I said, you have external storage, right. External storage is something, the terms that we use for them are typically either HDD, the hard disk drive, or SSD, solid state drives, right, or flash drives. Those are common terms for what we call external storage. They are typically even much slower than dynamic RAM, but the capacity is huge. Terabytes are easy to obtain, right. I mean, even a fairly low end laptop these days, for that matter even some phones, end up with terabytes of persistent storage. And that word persistent of course is important, right. What it means is that the data present in this external storage survives across, let's say, rebooting the system or switching off power and switching it on again, right. In general, it is what is called non-volatile storage, right. So if you power cycle, if you switch off the system and switch it on again, that data which is written into the external storage is expected to remain as it is, right. So the important point over here is to understand that because of this hierarchy in terms of how memory gets implemented, there are trade-offs involved. Ideally, for a CPU, we do not want this kind of a hierarchy. In the ideal scenario, I would always want my CPU to be able to access any address or any location that it wanted in a single clock cycle, right. And that's actually something important to keep in mind. The reason why we have different kinds of storage and all of these different concepts like files and caches and external memory and other things are because we do not have that ideal scenario where the CPU can just fetch any data in a single clock cycle. If it did, then you pretty much would not need many of these things. It would simplify a lot of the design aspects of computers as we know them today, but it doesn't exist in practice, right. So we have to make do with what we have. So, given that we have this large amounts of external storage, right, one of the problems with this external storage is that even though it is in principle what we can call random access, right, meaning that I can access any element inside the storage in pretty much a fixed amount of time, right, it turns out that that time is actually pretty large, right. So, if I were to directly try and access arbitrary elements in external storage just by trying to assign a unique address to each and every one of them, it may be theoretically possible, especially with 64-bit machines, because they have a very large address space associated with them, but it would not be particularly helpful, right, and it would make your life quite difficult in terms of keeping track of the addresses required to access different locations on the external storage. So, instead of that, what is done is that external storage, SSDs, HDDs and so on, are organized differently, and the operating system handles all access to this data, right. Now, we have already seen that, as in the case of dynamic memory, the operating system is also involved in giving you access to DRAM, right. So, let us say you want to create a large array in memory, you would call the malloc function, and the C runtime would then interoperate with the operating system and would finally figure out that, okay, this is a chunk of memory that is big enough to store the array that you need and give you back a pointer to that memory, right. Now, the operating system handles external storage at an even more sort of restrictive level, right. You cannot just directly go and access a particular location on, let us say, an external disk, right. What you can do instead is use certain function calls to say that you want to create what are called files, and the operating system will then decide where a given file is going to be stored in external memory, how the data is going to be stored, how it is going to be indexed, how it is going to be retrieved. All of that now has to go through certain specific function calls, right, and that gives us, at some level, it is a nice abstraction. It gives us a new degree of flexibility in terms of how we design systems. Effectively, what we end up with is something that we refer to as a file system, right. And the reason it is called a file system, of course, is an analogy with normal office spaces, right, where typically the files associated with a given project or for a given person are all kept together, right. Papers are put into files, files are kept in cabinets or folders, right. Files and folders are sort of related in an office context, right, and you have some kind of index capabilities that allow you to locate any of the information that you want relatively quickly. So, what that means is that you end up with some kind of a hierarchy. Just like in an office you might have a storage cupboard, the cupboard might say that it holds all files that start with letters A up to, let us say, G, right, and if you want to find out about dogs, you would go to the section of that cupboard that holds things related to the letter D. Under that, go look under DO, and in other words, there is a findable way or an indexable way of getting to any data that you want in an office or a filing system. The same kind of idea is used in computer files as well, right. So, what the operating system does is it gives you an abstraction that allows you to open a file, organize files into different folders, create a complete sort of tree structure, a hierarchy under which you can store things, and it need not be just alphabetical order, it may be based on other kinds of organizational needs that you have, okay. And the fact that the storage essentially becomes findable based on the name of a given file is the fundamental thing that a file system provides. In particular, there is no guarantee that I can find something based on the content of the file. In other words, if I want to find out all files that are present inside my computer that are related to dogs, the file system, normal file systems do not try and guarantee anything of that sort, do not sort of make it easy for you to do something like that. You need some other kind of searching index in order to answer a question like that, right. So, the purpose of a file system is that it assumes that the user has some kind of organizational structure in mind and that you are going to automatically partition your data into whatever hierarchy is required for that. So, what it does is it provides you with an abstraction called a named file, where you can create a file, assign a name to it, and later on you will be able to retrieve that file by giving the name. Okay. And files can now be organized into folders or directories, as they are sometimes called. And in some cases, you may have heard of things like the Amazon S3 or Google Cloud Storage. Those don't exactly have the concept of folders. They use something else called object storage, right, where in principle there is actually more associated with the file. It actually treats each file as an object that has certain data associated with it and provides a slightly different abstraction. But for the most part, this is the kind of thing that it's trying to do. It allows you to collect related data together, associate a name with it, and that name then becomes something, the basis of sort of indexing the entire system. So that, in other words, is the purpose of a file system, right? So if we think about it, what is it that we want over here? We want to be able to create a file with a given name and then to be able to open that file later and read back contents from it. As long as we can do that, we have some way by which I can get persistent storage onto this external storage system that I have. So the contents of a file can be in general arbitrary data, right? The name will have certain restrictions on it placed by the operating system. For example, you might have certain restrictions such as the length of a file name, right, or what kind of characters are allowed to be present in the file name. You can have a hierarchy created by having different folders, and that hierarchy is essentially called the entire hierarchical name that we use in order to get to a file is called the path of that file, right. Effectively what it says is I start at a given point which is called the root of the file system, and from there I follow a certain path in order to get to any given file. The file by itself can contain pretty much arbitrary data, right, and as I said, the important sort of concept to keep in mind over here is that everything related to files is controlled by the programming interface that's provided by the operating system. In the context of Linux and other operating systems, these are usually called system calls, right, which is basically the same as an operating system function. So we are sort of calling functions that are provided to us by the operating system or the runtime libraries. They are called system calls, and the reason they are called system calls is they usually require some intervention from the operating system itself, because you are now trying to access data which is on a different kind of storage, and a lot of things need to be checked before giving you access to that data. Do you have the right permissions? Does the computer in the first place have access to that data? How exactly does it get hardware access? How do you control when different programs are trying to access the same hardware at a given point in time, right? The bottom line is direct hardware access to a given SSD or a sector in an SSD is not permitted in general. You have to go through the operating system kernel, which is basically the core part of the operating system, right? So ultimately all access in an operating system happens through these system calls, which provide the programming interface required to access files, and that is what we will be looking at in terms of the examples later. Alright, so all that was very generic. It's not restricted to any particular programming language, nor is it restricted to a particular operating system, but we are interested in the C programming language, right? And the main thing that we need to understand over here is that there is something called a file in C, right? What is that thing? It's a struct, okay? So we already know what structs are. Structs are used in order to collect information related to one common topic together into one place, right? So the examples of structs that we saw was, let's say that there's a fruit seller. The fruit seller would need to, if you are writing, let's say, an inventory program for a fruit seller, you might have a struct that keeps track of the name, the quantity of a fruit, and the price per unit of the fruit. Now in the case of a file, there are many different pieces of information that I might want to keep associated with a file, right? The first thing to understand is, what does this even mean? Because a file is actually just a collection of bytes that is present in some external storage. So this file struct that I am talking about is not really part of the file itself. It is a separate piece of information, sometimes called the metadata, associated with the file, which includes things like the name of the file, the location where it is stored, things like Is it currently open? Can it be opened? Is it available for access? What are the bytes that are present that can be read from the file? Are you allowed to write to the file? If so, what is the current state? Is somebody trying to write to the file? All of that information needs to be saved somewhere in such a way that the operating system and the program that's trying to do all of this knows about it. All that information is, in other words, stored in this struct called the file struct, right? And pretty much everything that we do in C, right, at least in order to access files, is using something called a file pointer, which is declared literally as file star. Now, one of the things that you would notice that this is one of those rare instances in C where everything is in capital letters, right? FILE, the word itself is completely in caps. It's not a very common occurrence. Most things in C are in lowercase, right? Whereas this is one of those things which actually happens to be in uppercase. It's just that way, right? There's no particular reason why. And one other word or term that you might hear or come across in the context of accessing files is this word called stream, right? And the word stream is often used in connection with files as well. So, in many contexts you might come across this thing saying that you are trying to access data from a stream. And the idea of a stream is simple. It basically looks at the data that you are storing as simply a stream of bytes. What do I mean by a stream of bytes? One byte after another, just sort of flowing continuously, right, with no particular interpretation attached to it, right. So, I do not care whether it is a set of integers or whether it is a set of shorts or whether it is a set of floats or whether it is a set of structs. All I am saying is it is, a stream of bytes. So, the file pointer, in other words, is just an abstraction that is used by the C language to control access to this kind of system. Okay. And as we will see, the main thing that we will be using are going to be these two functions fopen and fclose that are used in order to actually gain access to the file, right. Fopen in particular is used in order to gain access to the file. Fclose is actually important for the simple reason that whenever you are done with using a particular file, you need to remember to close it. It is exactly the same as if you malloc a certain amount of data, you should remember to free it. Now, in both of those cases, the free as well as the fclose, if you do forget and the program exits quietly without doing anything else, in most cases the operating system takes care of either freeing up the memory or closing the file for you automatically, right. But there can be scenarios, for example, where the program crashes and does not really get a chance to clean up after itself. So, it is always good practice to make sure that once you are done with a file, you close it properly. Similarly, when you are done with malloc, you free it so that the memory goes back to the operating system for further use. There are certain concepts such as the permissions associated with a file, right. So, for example, who does a file belong to? Are you as a user allowed to read or write a file? There is also something called an execute permission, which means that are you allowed to treat a given file as a program and try to run it, right. That is not something that we will be covering over here because it is partly operating system specific, right. That is not part of the C language, it depends on the operating system that you are using. Now, as you might imagine, when you are trying to use files, there are a number of other kinds of errors that can also crop up, right. In particular, you can run into problems such as running out of disk space when you try to write to a file, finding that a given path is not present when you try to open a file. You could even have a scenario where a path exists at the time that you first look at it and then it disappears because, let us say, somebody removed a directory at some point, right. So, there are many different kinds of errors that can crop up when you use these file operations, and you need to be aware of them at least when you are sort of trying to create or use the operating system calls in order to access and modify files. Now, there are a couple of interesting so-called standard files or special files that are present, especially in Unix or Linux like operating systems, right. And these are terms that we will be encountering again later, so I am just sort of mentioning them at this point. There is this concept of what is called the standard input, right, which is usually referred to as std in, the standard output which is std out, and there is another file called std_err or the standard error. So you have already seen a number of examples where we have started a C program with the first command being #include stdio.h, right, and so far I have just mentioned it as we are including a header file which contains some definitions and so on, right, and stdio is just because of this, it is the standard input and output, and a lot of the definitions associated with files, including the concept of the file struct itself, are ultimately sort of pulled in through the stdio.h header file, right. So, it is part of the C runtime, and all of these things std in, std out and std error are defined within those header files. These are things that can be used in different contexts. Once again, what is the purpose of these standard files? It is just something that is provided to you by the operating system when you actually start running any C program. Once again, some of these things are sort of slightly specific to Linux, but on the other hand, std in, std out, std error are also sort of considered part of the C language itself, and they are pretty much standardized at this point, and therefore are always provided to you in any system that you work with. So, just to sort of show you the most basic functionality, right, which can be used in order to open or connect with a given file, right, I am looking at a very sort of trivial example out here, where basically what we do is we declare a file star fp, right, it is not been initialized yet. So, fp is just a pointer to a file struct, but it does not really have a sort of definition yet at this point, right, it does not have a value. So, what I try to do over here is I am going to use this function called fopen, right, and what I do is I give it a file name, and I also give it something called the file mode. So, this R over here within quotes is what is called the file access mode, right, and R basically indicates that we want to read the file, right. In particular, as we will see later, this refers to something called text mode access, but we will get to that later. Primarily what it means over here is I am trying to read from this file. Now, what happens over here is that fopen, the function call, will try to open the file, and if it succeeds, it will return a file pointer. What do? We basically straight away assign it to fp, and I have this kind of shortcut out here where I basically say that immediately after assigning, I am going to check the value of that assignment against null. So, what does this mean? Remember that in C, when you assign something a is equal to 3, a of course gets the value 3, but in addition to that, that a equals 3, the value 3 is also the return value of that entire assignment expression. In other words, an assignment statement is actually an expression in C. It has a return value of its own, right. So, what we are doing in other words is we are writing this as a kind of shortcut. I call the fopen function, I assign it the result of that into fp, and I check the result straight away by comparing it against null. The reason I compare against null is if the file was not there, or I did not have permission to open it, or for whatever reason I could not access it, the file open, the fopen function is going to return a null pointer. So, you should always check that value, right. In this case, what I have done is I have actually given a file name that does not exist. How do I know that? I can go to my shell over here on the right hand side, and if I type ls, I can see that there are a few files present out here. Well, in this case there is main, which is the actual compiled output. There is main.c, which is the file that you see over here in the left hand side pane. There is a make file which is used for compiling main.c and creating the main output. There are a few other files that we are going to ignore for now. The important point is if I look for a file called notest.txt, that does not exist on the right hand side, okay. So, what happens when I actually try to compile and run this function? Let us try running it. It basically compiles, and you can see that it basically prints out a message saying failed to open file. So, in other words, what happened is I tried opening, I went through this process of checking it against null, and it turns out that FP actually got the value null. So I print out this message saying failed to open file and return. Now what happens if I actually give it the name of a file that exists? I can put in this thing saying right, I am just printing out a message saying open the file, right, nothing else over here. And when I run this, of course right now I have not changed the name of the file, so it remains this way, but if I change this from no underscore text to just test.txt, because I know that there is a file called test.txt out here, let's see what happens when I run this. Now the message has changed, it says open the file, right. So this was a very very simple demonstration. Its only purpose was to show that you can open a file for reading by using the fopen function call, right, and that function call returns a pointer. If it failed to open, it will return a null pointer, and you should always make it a habit to check whether it returned a null pointer and to do something appropriate if you could not open the file, because if you proceed without doing this, right, let's see what happens over here. If I do not return at this point, right, if I continue and if I try running this in this way, what you can see is that it actually printed out the message failed to open file, but if you look closely over here, you will also see that the exit status was -1. Let's understand that a little bit better, right. I can go to the shell and actually explicitly execute the command by giving /main, and you can see that yes, it printed out failed to open file and then promptly gave me a segmentation fault core dumped, right. So hopefully you remember that segmentation faults happen when we are doing something inappropriate with memory, right, trying to access memory that we are not allowed to. And if you think about it, that is actually what is happening here. I am trying to run an fclose on a null pointer, right, and if I try to fclose a null pointer, that is a segmentation violation and should basically give me this error that I see out here. Okay. So you need to be careful when you are trying to access files. In general, always make sure that you check the return value, and once you have checked it and once you have finished using it, make sure that you close it, but close it only when you are actually done with the use of the program of that particular file.